Okay, cool. So we'll get started. Okay, Lab5, right? That's the one with the ADC and stuff and blinking LED. Good. Okay, Lab5. Anyone working on that extra credit for that? Anyone think that they can get the fastest communication speed? Yeah, I've noticed that no one has tried for it yet. So at the moment, even if you have like 1 character per second, you'd be in first place. So maybe go and reach out to a TA, be like, hey, can you time me? Yeah. Okay. So just wondering, have people been having like troubles with it still? Like, are you still kind of debugging anything with it? Yeah. Okay. So I'm guessing probably the people who are here today maybe have already figured out the LED and whatnot, but I have been getting a lot of questions about it on Piazza. So at least I want to go over more specifically the circuit that you need to assemble in order to get the photodiode working properly. And this may be different from how you did it, but I want to introduce just a short little explanation of how it's supposed to work. I'm figuring it out kind of at the same time as you guys are. So I did build this circuit. So let's take a quick peek at this. Okay. And it is focusing. Good, perfect. Okay, so here we can see that I have, you can see, so pin 2, which is right there, is being hooked up to this resistor, which you can see, what is the other end of the resistor hooked up to? Pin 2? Yeah, perfect, so it's hooked up to ground. So by default, so if we did not have this wire plugged in right here, then what would the ADC read out? Yeah, perfect. Okay, so the ADC, assuming it was on pin 2, would read out 0. Okay, I guess now question. So if I now take this wire right here, which you can see is hooked up to, what pin is that? Can you see? Yeah, 3.3 volts. If we now go and hook it up to this, then now what would the ESP read out? If we hook it up to pin 2.
4096.
Yeah, sure. So it would read out like 3.3 volts. Good. Okay, so good, so that's how the ADC works. Okay, now let's go and see what happens when we hook up the photodiode to this. Let's see if I can unplug. Okay. So, so here you can see photodiode, good. And let's first just see what happens if we hook it up without powering it. So if we, what we can do is, I guess we could put it in parallel with the diode, or with the resistor. So we could put ground, like right there. So let me show you. So you can see the long end, this is the side that you should connect to positive. So, okay, so let me go and put this in. Okay, good. I'll go and hook up the ADC to the positive end. Let's see if we can just read out any sort of voltage now on the positive edge when we shine a light on it. And I'll go and hook up ground as well. So effectively, yeah, what's happening is we are just checking if we shine a light onto this LED, if there's any sort of voltage that comes through this. So what we can do is I'll go and run the ADC example.
Wait, what's the resistor value you used?
I just used just whatever Bell's provided, and I did find that worked okay. Yeah. If you need more current, you can always just put 2 resistors in parallel. Yeah. Okay. Good. Oh, perfect. Okay, good. So we can see that, let me turn off this light, actually. Okay, cool. So once again, okay, you can see that it is roughly, I guess, at like, whatever, 6 to, I guess we could scroll up a bit. So you can see it's like 6 to 13 millivolts. Okay. And if we go and shine a light on the LED now. Okay. Then you can see that, well, actually, like maybe it's a little bit higher. Now it looks like it's spiking up to like 16. Okay. So by just putting this photodiode, like just directly hooking it up from ground and like measuring the voltage that is generated on this, you can see that like it's maybe just a few millivolts, but there is some extra like kind of voltage that is provided when you just hook it up straight to ground. But you actually do need to provide some extra power to it in order to get like the current like kind of properly working. So instead of just hooking it up straight into just the ADC, let's go and see what happens now when we power like one side of it. Okay, so I will now modify this circuit. And so instead of, I'll go and unplug it before changing it. So now what I will do is, so I'll leave this resistor in, so it's now by default pulling it down to ground. And then what I can do is say that this side will be now powered. So the positive side will be powered, and let's just power it with 3.3 volts. Okay, and then we can take the other side and, should we plug this other side into ground? Or where should we plug it into? Should we plug it into ground?
GPIO 2.
Yeah, GPIO 2. Okay, what happens now if we did plug it into ground right now?
We'll just short it.
Yeah, it would short it. We would have 3.3 volts flowing through the diode. It would be shorted to 0, and our diode would burn up. Yeah, so very important. So do not ever hook up power like directly to the LED or to the diode. Instead, what you want to do is hook it up through a resistor. So we're hooking it up through the resistor, which is then hooked up to ground. So now we can go and plug it in. And there we go. Okay, so in theory, that should now be better. Let me go and repower this. Okay. And there is like current protection kind of in place just in case you do like short any of the pins, like put a bunch of current through pins. But generally, it's always good practice go and unplug your development boards anytime you like try unplugging things and moving things around. So let's now see. So at the moment, it looks like it's basically the same. But now let's see, so if we go over and shine a light on it, let's see, does it go up? Yeah, so it looks like it goes up like significantly more. Right. Okay. Well, yeah, it's kind of interesting because there is a little bit of a voltage that's generated when just by the diode itself, but by shining a light on it when it's powered, that's when you get the greatest current through it. So cool. Okay, let's see what happens if we flip around this photodiode. Now I'm curious. Okay. So what we have right now is we have the positive side hooked up to power. Let's go and just flip it around. See what happens. Okay, any theories? Do you think it's just always going to be 0? What do you think? Okay. Let's see what happens. Okay, so at the moment it's about 0. Let's go and shine a light on it. Okay. That's interesting, right? So actually, it looks like the orientation of it almost doesn't even matter, at least for this purpose. Yeah. Okay. Cool. Good. So you can play around with that, and the exact specifics of how photodiodes kind of how they work kind of eludes me, but there we go. So at least now you need power. Okay. Was anyone build this circuit basically have power? I think there was a nice diagram on the board with TAs and stuff. Okay, fantastic. So now you know. Yeah. Also, there were some questions about whether we should power it with 3.3 volts or whether we should power it with 5 volts. So I don't know. We could quickly go and test that. So now what I can do is hook up this side to 5 volts and just see what happens. So okay, good. So we can see by default it's 0. And then when I shine a light on it, then you can see it goes up. Maybe even a little bit higher than normal. And if I now go and flip it around, so now you can see it's like in the middle for some reason. And if I shine a light on it, then now it actually doesn't go up. Or I guess it goes up a little bit. It goes up, I guess, by like by like 0.2 volts.
So
Yeah.
this is in the reverse bias configuration?
Right, yeah. This is when, let me show you. So this is when the positive side is hooked up to the power. Yeah. Cool, okay, so there we go. So I guess what we could say then is, like maybe I started out this explanation backwards then. So maybe, let's see. Yeah, so for some reason it looks like the orientation of this, I guess, when it's, I don't know, can we figure it out? I don't know. Can anyone come up for an explanation why when we have like this orientation, that for some reason this looks like it's about like, I don't know, VD, or what was it? It was like, I don't know, it was like about 2 volts. But when we went and inverted it now, it like worked. I don't know. Any thoughts? Zero slash, 2.3. Yeah. No ideas? Sure. We don't have any analog experts in the room. Sure. Yeah, any thoughts?
I'm guessing so I just looked at the data sheet. It has a
Okay.
voltage of about 1.3 volts.
Oh, sure.
And for current of about 15 microamps.
Uh-huh.
And I calculated that the current that's going to be sinking through that resistor compared to the current that's going to be actually provided by the diode in the configuration up top would yield about like 1.4 millivolts. Is that what we saw in the terminal?
Right, yeah, 1.4.
Yeah, so in this configuration, the diode would be passing about 11. Oh, actually, it's millimeters. Yeah, I don't know.
Okay, sure. Yeah. I don't know. Yeah. Sure. Well, I will say that this is often like a thing that kind of I do. It's just like the debugging strategy of just like, if I don't know what to do, I kind of just try a bunch of different options. And then usually I end up kind of just stumbling across the correct solution, and then like you can move on. This is genuinely like a very like solid kind of engineering strategy, is just like try a bunch of things until eventually it works. Ideally, you would then go and like learn how it actually works. So I apologize that I don't fully understand how it works, but I figured this was kind of a good enough thing to discuss. So, okay. Lab, yeah, feel free to ponder this more. I want to now mention, so Lab6, has anyone looked at Lab6 yet? Lab6? Cool, okay, great. So Lab6 is, I would say probably, in my opinion, probably the easiest lab of all of the labs. Maybe not necessarily like if it was the first lab that you start with, but just because of like how much harder the other labs have been in comparison. But okay, so what I wanted to do is just like briefly go and pull it up, just so we are all on the same page about what this is. So what, I guess it's, okay, cool, okay. So here is the ultrasonic range like sensor. Okay, anyone used one of these before or seen one of these before? So what this is effectively is just a kind of a speaker
that is meant to work at really high frequencies, and then you have a microphone that's meant to work at really high frequencies. And what this does is it will kind of like just shoot out just like a sound wave, but it's like really high frequency to the point where it's like really hard to hear or like impossible to hear. And then what will happen is if you put something like near it, then the sound will then bounce back, like that comes out of the speaker, will bounce back and then enter the microphone on the other end. Then what can be done is there can be a comparison that is just like how long did it take for the data to be like sent back, basically. So we'll just, I believe it does like a chirp thing, so it just like does like a frequency, what do you call it? Sweep. Thank you. It does a frequency sweep, and then eventually it'll, when the data is sent back, it will figure out like kind of exactly like how far away the object is. Yeah. And this device uses I²C. So overall, going to be pretty simple to get working. And we can take a look at the lab. So okay, so yeah, here in this lab, so all you will need to do basically is just go and use the ultrasonic sensor to measure out the distance from like any sort of device or any sort of like obstacle. So what I would probably do is just take like a laptop like case or something and then use that to measure. And this probably gives you kind of the best like bounce back that I've seen. Yeah. Anyone got this working yet? Yeah, so I recommend starting it early just so that you're done with it, but also it is probably the easiest lab. And I'm not expecting to spend that much more time talking about this. Yeah. Cool, okay. What I will spend a fair amount of time talking about is actually the following lab, which is Lab7. So Lab7, in my opinion, is probably the hardest lab. So this is why it's last. And actually, I'm going to start talking about it like today because it is important that you all probably like start this probably like this week. So weather station, I will say like last time I taught this course, I think only about a third of the class was able to complete this lab. So please make sure that you like actually start this early and work on it. Effectively, what this lab is what you will do is on the ESP, you will collect the temperature and humidity sensor, but then you will also go and query another like server using HTTP, and you will fetch in weather data from the internet, like all within the ESP. So you're not like using the Raspberry Pi, not using your computer. Instead, the ESP itself will send out like HTTP requests, and it will fetch like the weather data, and then it will receive it. And there's this cool website right here. So where is it? I just saw it. Yeah, sure. So here's this cool website that is it's open source. And I want to just quickly kind of pull it up. Okay, that's annoying. Okay, sure. So and actually, I'll do this. Okay, that's fine. That's fine. So if we pull up the GitHub page for it, so we can see that this this project, what it will do is it will fetch, or it will produce the weather data just from like publicly available data from all sorts of different sources. So like Paris, they have their own kind of like open like weather data that they're just like constantly publishing like through all of their just sensors that they have around the city. And then what this project is doing is it is just keeping track of all of like the publicly available weather data. And now anytime that you do anytime that you fetch that data, it will then give you the weather at whatever location you want. So if we go and actually run this command, so curl, anyone used curl before? Curl, so this will get the data from a URL. So we can go and curl this data. So let's just see what happens. So if I go and curl this, and there we go. So you can see it like immediately fetched all this data. And we can see, so it knew our location, and so it fetched the data for Santa Cruz. So in case you ever wanted to check the weather and you don't have a desktop environment installed, you're welcome to just go and do curl wttr.in. Yeah. There are a bunch of other little commands that you can do. And I believe it talks about this. Yeah, so if you want, you can fetch the weather data from different cities. You can also fetch data using GPS coordinates as well. I think that's in there. You can just fetch in a nice kind of formatted way. You can grab just the temperature data, or you could just grab the humidity data, or just the wind data without needing to parse out the the nice kind of human readable format that it gives you here. You can just get those single integers back. Okay, so I guess the question is now how do you curl now, except from the ESP32? It's the ESP32 doesn't have a terminal where I can just type in curl. Okay, so any thoughts? How can we fetch internet data using the ESP? Yeah.
Send a GET request.
What was that?
Send a GET request.
Sure, a GET request, but I guess that falls into HTTP. Can we go I guess a little bit before that?
Open a TCP socket.
Sure. Okay. So opening a socket. What is a socket? Anyone heard of sockets before? Okay. Sure. So sockets are a networking concept, but this is also kind of produced by the operating system. So I guess even before that, what does if you wanted to let's say you were writing Verilog, right? You're writing Verilog and you're designing a your own processor. Now your boss comes up to you and is quick, I need your processor now to work with HTTP requests and be able to fetch data from the internet. And what sort of things would you need to add to your hardware? Yeah, what was that?
Some sort of internet handler.
Sure, yeah, an internet handler, yeah. So maybe you'll probably need to have some sort of Ethernet layer or something, yeah, and you'll need to have at least some sort of maybe software development interface to whatever user. So yeah, so as was mentioned, so sockets are a cool abstraction for internet. So actually, we don't need to know exactly how the ESP is able to send data to the internet. Instead, what we can just do is create something called a socket. And when we create a socket, it will basically just write out to our kind of magic internet implementation. So what's really nice is the ESP actually has a example of getting HTTP working. So I want to quickly pull that up. Okay, let's see. So good. So here's ESP IDF, and if we want to see how to actually fetch data from the internet, there is an example of how to get HTTP working. And so you can see, so it's in examples, and then it's in protocols, and then HTTP request. And then so this code right here shows you everything that you need to get working in order for the ESP to fetch data from the internet. And so what this example right here will do, just starting out, is it will fetch the data at example.com. So let's go and actually open that and just see what happens when we go to that website. So okay, so here is example.com. Right, not too exciting, but let's just see if we can in fact go and fetch this this website from our ESP. So okay, so let's go and look it up again. Okay, and flash monitor. Okay, so there's an immediate issue that we run into, right? So I guess the issue, sorry, one sec. So the issue is, well, we probably need to somehow connect our ESP to some sort of Wi-Fi or some sort of internet, right? We can't just expect that it's going to work automatically. So in this case, what we'll need to do is actually connect we'll probably want to connect to Wi-Fi. And for that, we can go into SDK defaults. Where is it? SDK config. Sure, it's probably fine. And you can see, so starting out, it looks like it is using Ethernet, but I think there's a way that we can get it to use, use Wi-Fi instead. So let's see. So I think we can do. I'll make a .defaults. I think that will be useful. Okay. So in order to get this working with Wi-Fi, what you will need to do is type in config, example, and it's Wi-Fi. Let's see. SSID equals, and then you put in the name of whatever like you're trying to connect to. In this case, I'm going to use my hotspot because I think that will be easiest. And then for Wi-Fi, say password as well. And I will go and so where's yeah. Okay, so I've just gone and enabled my hotspot. So actually, let me go on my computer. Let me see if I can connect to it really quick. Just make sure it's working. So okay, so here's my hotspot. So you can see ES iPhone, very exciting. So let's go and put that in. So it's E.S iPhone. Okay, and my password, temporarily, at least just for this example, is I believe password 7. Okay, so if you want to hack me, now's your chance. So, okay, so and that is all we need to do. And then in theory now, when we go and compile this, it should just automatically connect to our hotspot, or my hotspot. Okay, let's calendar. Okay, fantastic, good. So what you can see, so it looks like it successfully connected. Now it says Wi-Fi disconnected. All right, well, okay, what's going on? Connecting, what? Threshold, wait. Why did that happen? No. What? No. Well, what if I just try again? Okay, so if I go and reset. Yeah. Well, okay, I don't know why this isn't working. It was working yesterday. No. Okay. Well. Great. Okay. Well, imagine that this worked. Okay. And what you would have seen, maybe I'll go and double check if I'm missing anything. What you would have seen is it would have displayed out all of the data that it fetched from example.com, and you would see like the full like HTML like code that took place. So what I want to like quickly do is if I scroll through this, so in order to actually like grab this data, so we can see, hold on, let's see. Yeah, okay, so right here, so what we do is in order to get the internet working with our ESP, what we need to do is do a write command. And what write is, this is generally used for files. Like generally when you want to write into a file, what you do is you call write, and then you put in like whatever bytes. Usually maybe there's a layer of abstraction above that. Maybe it's like if you're using C++, use like IF stream or something, or I guess OF stream. But for writing like the lowest level, you use something that is provided to you by your operating system. By like, I guess in this case, it would be like ESP IDF. So they provide you write. But notice, like we're not actually writing to a file. Instead, we're writing to this like S. And what this S is actually, like you can see when it's opened up, this is actually a socket. And so this is how we can connect to the internet, is by, all we have to do is just open a socket instead of like opening a file. So instead of saying like S equals like, open, like, and then a path to something. Instead of doing this, we just say like this now, like treat this as if it's a file. And now what we can do is we can write out to the contents of this. And this is a very kind of common strategy in operating systems, is any time that you want to have some way to interface with your, with the hardware that is connected to your device, what you do is you kind of just treat it as a file. So like actually, like for example, like if we wanted to like read out this data right here, like you can see that the ESP is sending us all of this data. Okay, but if we actually like want to like if we wanted to now not use like IDF monitor, but instead like read in this data, then I believe what we can do is, so if I go and kill this, so what we can do is we can like list all of the like USB devices that we're connected to, and we can just like read out the contents of like this device's like file. So let me quickly show you that. Let's see if I can find the location of this. So if I go in ls/dev/tty, let's see. So I got a lot of TTYs, but I think it'll be this ACM0. So if I go and cat this out, I guess not. Let's see. So what I can do is I can unplug this and then see what changed. So if I do TTY, yeah, okay, well that was it. So I don't know why it didn't work. Well, we could also just connect to it using a serial monitor, which effectively is just the same thing. And oh, it's because I just connected it. Let's see. Okay, yeah, so it is ACM0. I don't know why it wasn't able to read out the data, but that's okay. So what we can do is if we now open up this file, so you can see the file is called /dev/tty ACM0. So this is from the operating system's perspective. Like this is a file, and if we go and like read out the contents of this file by like click Start Monitoring, then you can see that we should start receiving. Yeah, so we start receiving like, oh, like Wi-Fi disconnected. Like this is just the message that our ESP is like trying to send to our computer, which is like kind of cool. Like if we now wanted to like, yeah, if we wanted to now send data to our ESP, all we would do is just now write to this file. Let me try one more time. I think, I don't know, if I just go and like cat this out, usually it just like works. Let's see. Oh, well actually now it seems to be, oh there we go. Okay, I don't know why it wasn't working. So cool. So you can see like cats. So usually cat, what does cat usually do? What does cat do? Like if I don't know, if I did like whatever is in this, if I cat out like the README, right? Then it will print out the contents of that file to to the screen. But if I now go and just cat out now like this file, then now we see that actually like it's this bit of hardware. Pretty sick, yeah. So that is exactly what is happening here inside of this this example. When we like write to this file, but it's actually a socket, that is how we send data, I guess, out like to the internet. And we can see it, so we're sending out this request, and this request is actually, it's a HTTP GET request. So if you're familiar with HTTP GET requests, then that is what we are writing out to our internet like hardware that is baked into the ESP. Cool, and I think somewhere we read from, oh yeah, good. And then here we go. And then here we can see we read from the file, which is of course the socket. But when we read from it, then we take this content, and this is the HTTP response. And this is where, if the example is working, this is where it would have said like, oh, example.com source code, like welcome to example.com or something. And then it says like, oh, done reading from socket, and then I think it tries again. So there we go. Yeah, cool. So if you now wanted to make your own driver or something for a device, then like if you are making your own PCIe device or something, then what you would probably want to do in order to like make your device seem like useful for people, what you would need to do is you would just make your device, like you would make it so that anytime you plug it in, effectively the user will just treat that as a file. And now if they want to write out to your like PCIe device, if they want to write out to your graphics card or something, if they want to write out to your Ethernet controller, then now they basically just open a file and then write a bunch of like words to it according to your specification. For example, maybe they send out like a HTTP GET request or something. And then in the documentation, you just say like, oh, and then expect later, you can just read out the contents of that file, and that will give you like effectively what was run on the hardware. Yeah, cool. Does blow anyone's minds a little bit that you can just like cat out like this like weird kind of looking thing, and then it gives you the hardware of itself? Yeah. Yeah. Okay. Cool. Yeah. Any final questions on this? Yeah.
Is there a way to do it through the serial connection, sending an HTTP request or any sort of request like that?
So I guess what I'm doing right now is I'm connecting my computer to the ESP. That's what this is.
Yeah.
Separately, the ESP has this like open and like read and write commands, which is for the hardware baked into the ESP, which is like different.
But there's no way to communicate through the serial connection and then have your computer send out?
I get, yeah, so what you would need to do is you would probably just, like you would need to read in constantly from like UART, like your ESP would read in from UART, and then it would immediately send out that data to the socket. And then maybe any read responses from the socket, it would now send it back over UART back to your computer. Yeah, so I guess you could do that, but you would need to write like code that would like interface between the UARTs and the socket. Yeah, sure, good question. Yeah. Good. Let me see. Yeah, I guess it's kind of just like last super quick thing. Do I have cable plays? So I did mention this a couple weeks ago, but I do want to just quickly say it again because it's kind of in the same sort of idea. Okay, so here is an FPGA development board, and you can kind of just ignore the FPGA part. But specifically, what you have right here on this board, the icebreaker board, you can see that there is this chip right here, and if I tilt it perfectly, you can see that this is called an FTDI chip. That's because this is a company that makes, a company called FTDI, and what they do is they make this cool chip that automatically just handles like the drivers and things for USB, to where now like the FPGA is able to access the USB port as if it was just UART. So the FPGA is, it's kind of dumbed down the serial communication. Instead of the FPGA needing to worry about USB, now it can just worry about UART. So, okay, cool. Let me show you now what it looks like actually on my computer now that I've plugged this in. So if I go and ls, and I can say /dev, and then so tty, I don't know if tty stands for anything in particular, but tty are, these are all of the serial ports on my computer. So if I go in and like list all of these, you can see, I guess, hold on. So here are all of the serial ports on my computer, which is honestly like kind of funny because serial ports have not been used for like the past like, I don't know, 10, 20 years. Like it's very rare to find a computer with a serial port on it still. It's like kind of this old kind of big blocky standard. But it looks like I have all of these devices right here that are like serial ports. And that is because serial is like really easy to like work with. So what like driver engineers, what like firmware engineers will do is anytime you plug in hardware and they don't worry about speed too much, what they'll just do is they'll pretend like it is a serial port. And so, for example, like the FTDI, what that does is it pretends, like you can see it's a serial to USB like adapter. That's what the FTDI chip is. And if I go and like, I guess there's not anything actually like being sent out on the FPGA, but by plugging in the FPGA, the drivers on my computer automatically discovered like when it did like the USB handshakes. It's like, oh, like hey, FTDI, I know you. I'm going to now go and create this like file on the computer. Now anytime like someone goes and writes data into this file, then the drivers will instead convert that like data that you wrote into that file, and it will convert it into a USB signal, which is then sent to the FTDI. So yeah, kind of cool. So if you wanted to make your own like FTDI chip that like goes from like I don't know, just any sort of data. Like if you want to send data out to something using UART, then what you would probably want to do is you want to have a driver that like pretends like there's a file that was just created that that now a user can write to. Good. Okay. So that is my kind of summary on that. On Monday we will continue talking about HTTP and whatnot, but I think it's probably a good enough place to end unless there are any questions on anything. Okay, cool. I will see you on Monday. Have a good weekend.